What if the greatest cities of tomorrow had no streets, no floors, and no sky, only endless space in every direction? Picture a home where up and down don't exist, where farms float in the air and rivers curl through the void. When we think of space habitats, the first image that comes to mind is usually a great rotating wheel or cylinder, massive structures like O'Neill cylinders or Stanford tori, designed to spin and give their inhabitants the comfort of gravity underfoot. These are iconic for good reason. Humanity is a gravity-bound species, and zero-G has proved to be less than kind to our bodies. Yet, not all visions of the future rely on spin. Some engineers and dreamers imagined habitats that embrace the absence of gravity, rather than working so hard to recreate it. The idea of a bubble habitat, a vast pressurized enclosure floating free in space, goes back nearly a century. John Desmond Bernal's 1929 essay, The World, the Flesh, and the Devil, gave us one of the earliest visions, a spherical space habitat intended not just as a station or waypoint, but as a genuine community adrift among the stars. Unlike the rotating designs that followed, including updates to the Bernal Sphere to add spin gravity, Botero originally envisioned people adapting to microgravity itself, enjoying homes and fields and environment free from weather and even free from the tyranny of up and down. Later, Danny Eder and others expand on this with concepts like the Eder Sphere, balloon-like megastructures on the scale of entire planets, as did Larry Niven with ideas like the Smoke Ring, a huge naturally occurring Dyson swarm of air in which asteroids floated around carrying life. Bernal's original version is probably not a place most of us would want to live. The ideas for the habitat definitely stirred imaginations, but on deeper consideration, it isn't practical and was more of a tangent inside a broader essay about radically changing society, and it included his belief that future humanity wouldn't care much for houses or walls. That essay ranged widely, from wireless power and transhumanism to hive minds and space habitats, blending together with his own political and philosophical views. There was a deeper philosophical angle here, too, for humanity's future. We humans are quick to assume gravity is a necessity of life, but in truth, gravity has been the one constant that biology has never had to adapt for, until we left Earth. Microgravity is indeed hard on our bodies, as astronauts have shown us in recent decades, but it also opens doors to radical new forms of architecture, ecology, and civilization. Imagine homes where walls and ceilings are meaningless, where transport happens in true 3 dimensions, and where ecosystems float like underwater reefs, circling in bubbles of air and light. But gravity is not inherently necessary for life. It comes with plenty of downsides, and it's easy to envision life forms that evolved in the void, robotic life recreated that needs no gravity to function, or even humans modified to thrive in such environments. That would also mean modifying all plants, animals, and microbes as well. We'll spend some time exploring how organisms might grow and live in zero-G, and what changes we would need to make to support them. So in this episode, we'll be exploring habitats that bend and spin, bubble worlds, chandelier cities, floating ecologies, and orbital greenhouses. We'll look at what it means to live without down, how architecture and culture evolve in such places, and what kinds of megastructures might grow from that bold decision. Along the way, we'll explore the effects on ecology, the psychological and cultural transformations of floaters versus spinners, and the vision science fiction has given us of civilizations truly adapted to zero-G. The case for large microgravity environments. We'll be talking about the Bernal Sphere more in a moment, as our first big space megastructure idea, but before we get to that classic design, it helps look at some close-to-home examples, both in space and in time, that set the stage for thinking about large zero-G habitats. After all, the question isn't just can we live in microgravity, but also why might we want large microgravity environments in the first place? One of the most obvious answers is industry. In orbit, you are freed from the constant tug of Earth's gravity and the interference of its atmosphere, making construction and manufacturing far easier in some ways. We discussed this recently in our episode on zero-G manufacturing, where things like perfect crystals, exotic alloys, and fiber optics can be produced in purer forms than on Earth. A large orbital shipyard would be the natural extension of this idea. Vast pressurized bays, where a spacecraft could be assembled without cranes, scaffolding, or heavy-lift vehicles. Everything floats, which means kilometer-long trusses, delicate solar sails, and enormous drives can be maneuvered with relative ease. Also, nobody needs to wear a bulky spacesuit and if tools or pieces of the ship drift off, they bump into the wall at low speed, rather than potentially bumping into something else at super high relative velocities and setting off an orbital debris cascade, like Kessler syndrome. There are lots of things that work better in zero-G, and while we might want to build a small routine habitat for crews servicing such a shipyard, or some megatelescope or other zero-G megastructure, in a lot of cases, just as with the modern International Space Station, it would just be easier to have the whole complex in zero-G. Megatelescopes. Now, speaking of megastructures, while this often refers to space habitats, most places people live and work in space probably won't be megastructures, and more to the point, not all megastructures are habitat related. In the short term, one of the most important megastructures we want to build in space would be giant telescopes that could never function on Earth or even be assembled here. Telescope mirrors less than a millimeter thick but hundreds of kilometers wide work just fine in space, where there's no wind or gravity pushing and pulling on them. These megatelescope concepts go far beyond what we think of with Hubble or even with upcoming generations of Earth-based giants. Some designs call for liquid mirrors spun into perfect parabolic shapes, vast arrays of distributed satellites forming synthetic apertures, or even lenses made of metamaterials or manipulated swarms of particles. A particularly ambitious proposal is to place kilometer-scale or even continent-scale optics in deep space, creating telescopes powerful enough to directly image continents and oceans on exoplanets light years away. Others push the envelope further, with gravitational wave detectors like LIGO's planned space-based successor, LISA, essentially functioning on a different kind of megascope, measuring ripples in space-time itself across millions of kilometers. We deep-dived this in our Megatelescopes episode some years back, but taken together, these astronomical megastructures highlight why large-scale microgravity environments matter. They aren't just for living in, they are for seeing, building, and discovering. Industry may anchor us in orbit, but science and exploration will give us some of our first true reasons to think on planetary scales in engineering. But we also have megastructures for getting out of orbit, like orbital mass drivers, or space elevator-like launch tethers, and by default these places do not have or benefit from having lots of gravity. Asteroid Hollowing. Once you've launched away from Earth into deeper space, it might be worth asking why, and going to mine asteroids is a big motivator. You can eventually build or import a routine habitat to these environments, but it brings up another straightforward concept of just hollowing out asteroids instead of building a habitat from the ground up. You take an asteroid, dig out its interior, and use the bulk of the rock for shooting its radiation and micrometeorites, and for selling for profit. Now, folks will often suggest you go ahead and spin that asteroid up, generating spin gravity inside, but this is nonsensical. Some asteroids are solid slabs you could probably spin, but many are just piles of gravel, and if you spun to a significant spin gravity value, will simply fly apart. Indeed, we discussed doing exactly that inside a larger metal cylinder as a way of dropping dirt and regolith into an O'Neill cylinder you were planning to build. Now, inside an asteroid you are mining, you might go for a very minimalist spin to give just enough gravity that the plumbing works and the dust settles, but that might need to be less than 1% of Earth's normal to avoid wrecking your asteroid. You can also drill a cylindrical shaft into an asteroid and plug a rotating habitat into a slightly wider sheath. Smaller asteroids might house a single bubble or cylinder, while larger ones could contain entire chains of habitats or industrial complexes, each nestled safely inside the shell. This approach is a practical stepping stone toward more ambitious designs and will likely be used by the first serious waves of space settlers. Even so, much of an asteroid's interior would remain wide, open zero-G spaces where people would spend much of their time. Since asteroid mining is often seen as the first major economic boom in space, and would initially be done in zero gravity for reasons of practicality and cost, there will be strong incentives to adapt to microgravity rather than avoid it. The miners and settlers in these places might even prefer the freedom of zero-G and come to see it as natural. Indeed, most spin gravity habitats are expected to include low gravity or weightless regions anyway. The end caps of an O'Neill cylinder, for example, curve up toward the axis, where gravity steadily drops off. Zero-G zones attached as ancillary structures would be normal features. For children raised in space, being comfortable in microgravity might be as natural an expectation as learning to swim is for those raised near lakes or seas. The Bernal Sphere. To most folks talking space habitats, the Bernal Sphere is actually discussing the spin gravity version of it later developed by Gerard K. O'Neill and others that Bernal's impractical vision inspired. And it did have a lot of practical issues besides being a no-gravity structure, which we detailed in our episode on Bernal Spheres. but it was only impractical in terms of lacking spin gravity because we assume human and other terrestrial organisms need gravity to function. Which we obviously do. We also need air to function, so all these zero-G megastructures we keep discussing are assumed to be pressurized with normal Earth air or a partial pressure oxygen environment. Nonetheless, we can contemplate vacuum structures where people have been modified not to need to breathe, or at least to do so from an internal supply. Those are not of interest to us today, but it highlights the practicality issue of the original Bernal Sphere was the absence of something we might be able to adapt to doing without, and might be glad to do so. Gravity tends to weigh on us heavily, so why bother with it if you don't need it? Or again, why bother with so much of it? And we have designs today that are very low gravity too, not just actually zero-G or microgravity. Bernal imagined a giant hollow glass-like sphere about 10 miles or 16 kilometers in diameter, transparent, crystalline, and floating in space. Inside it would be filled with atmosphere, sunlight, and freely drifting communities of people. Unlike later designs that rely on spin to simulate Earth-like gravity, Bernal's vision assumed humanity would learn to adapt to life without it. In his view, walls and houses would become unnecessary. People would simply live and work in open space within the enclosure, their belongings and farms secured in free-floating arrangements. That said, such communal openness is not strictly necessary for the design. Those of us who prefer a bit more privacy could still have personal dwellings inside the greater sphere. Instead of a traditional house, one might live in a floating ring, cylinder, or bolo-shaped module with modest spin gravity. Something house-sized spinning at walking speed could generate a few percent of normal gravity, enough to keep you on your bed at night without straps or to hoard items on shelves without magnets, though I think magnetic clasps and bottoms would be common on most objects. Larger or faster spinning dwellings could produce stronger gravity, but even a gentle pull might be sufficient for comfort, while the broader environment remained weightless. Ederworlds. So how big can this go? There's a couple directions that allow truly epic size. Ederworlds, sometimes called bubble worlds or Ederspheres, are habitats on a scale so vast they make even O'Neill cylinders look modest. The idea came from Danny Eder, who asked a simple question: what's the largest orbiting habitat humans could build? Instead of relying on spinning walls and structural strength, his insight was the gas itself has mass and generates gravity. If you trap a giant cell of hydrogen or other light gas, its own self-gravity can counteract the pressure trying to blow it apart, which is the case for most gas giants and stars, of course, while in this case an outer shell or cap floats upon it, containing the atmosphere within it but not under any great strain. The result is a self-gravitating bubble, a habitat where gravity and pressure balance each other out without requiring impossible materials or tensile strengths. Scaled up, this creates megastructures tens or even hundreds of thousands of kilometers across, soap bubbles in space. The default concept calls for a sphere not much smaller than the entire Earth-Moon system, just under 500,000 kilometers in radius. This is surrounded with a mostly hollow steel shell a couple thousand kilometers thick, with about 50 meters of thick steel shell on the extreme outside, serving as weight against the hydrogen gas and protection against radiation and micrometeors, and enemy attack for that matter. Gravity varies with depth, and indeed is much lower inside the inner shell as most of the gravity is coming from that steel shell, and doesn't count toward the gravity in the inner volume. As a reminder, any evenly distributed shell of mass generates no actual net gravity on things inside that shell, so a shell of vast mass but hollow would let you float around inside it in microgravity. The gas inside that shell does exert gravity, at least at depths lower than the object being pulled on. But in the primary habitation shell on the outside, with the steel exerting gravity, you're looking at about 2% of normal Earth gravity. The surface area of this sphere is more than 10,000 times that of Earth. A single Ederworld is expected to have multiple layers in open environment, and could have more living area than 1,000,000 Earths, with its interior atmosphere stacked in layers dozens of kilometers thick, like Earth's own atmosphere or even thicker. While the gravity inside is weak, it is not non-existent, and the design allows for countless sub-habitats suspended in the airy depths, floating cities, ring dwellings with spin gravity, or entire artificial ecosystems. Bubble habitats. Now, a variation on the Ederworld is a simple bubble filled with breathable air and moisture, and floating or suspended habitats or rocks, and this works easily and intuitively enough at smaller sizes, even into several hundred miles across. But let's consider way bigger. If you want an environment with 1% of Earth's normal gravity near its surface, and without a big thick shell filled with normal air at normal density, then you again have an object similar in scope to the whole Earth-Moon orbit, with a radius of 286,000 kilometers. This is only a mass around that of Neptune, 20 Earth masses, but spread over space 4 times wider or 64 times larger in volume. Your issue with this scale is keeping it from collapsing into itself as a gas giant, and a rather weird one of oxygen and nitrogen rather than mostly hydrogen and helium like natural ones. Your real issue here is that you don't need vast depth. About 1,000 miles of air is already immense. Think of a parallel to our earlier hydroshell concept, where a hollow shell is covered in a vast ocean. In this case though, you'd have 2 concentric shells with air sandwiched between them, separated by about 1,600 kilometers or 1,000 miles. That's an order of magnitude deeper than Earth's atmosphere, with the inner shell itself spanning some 2.2 million kilometers in radius, over 3 times wider than our Sun, using around 20 Earth masses of air. At the top of this atmospheric shell, which we might call an atmo shell or bubble shell, gravity would be just 0.0168% of Earth normal, fading to near zero at the bottom. Still, it's enough to build all sorts of suspended habitats, rocky platforms hanging from the ceiling or structures rising up on pylons from the floor, stalagmites and stalactites or chandeliers. It's an environment where up and down lose meaning, yet the faint tug of gravity gives just enough anchoring to work with. To put that in perspective, a person with a mass of 100 kilograms, about 220 pounds, would weigh just 17 grams, roughly 4/100ths of a pound. Drop an object from head height and in a vacuum, it would take close to a minute to hit the floor. In air currents, it could drift far longer. And remember, that's in the strongest part of the gravity field, right at the top of the shell, so you could definitely strap on a pair of wings and flap around. I think you would spin these slowly too. One this size could not be spun once a day without creating a huge centrifugal force far stronger than Earth's gravity, but in an outward direction. Growing food in zero-gravity bubble habitats might look wildly different from farming on Earth, but whether you're cultivating in space or on the ground, good systems matter. And as someone who lives on a small farm and keeps chickens myself, I know how much good stewardship matters. That's where today's sponsor, Farmkind, comes in. Farmkind is a non-profit donation platform helping people make a big, measurable impact for farmed animals. They research and identify the most effective charities working to fix factory farming. And unlike many groups, Farmkind is completely non-judgmental. They don't tell you what to eat. They focus on simple, strategic donations that genuinely help animals. They're also very clear about how your support makes a difference. Farmkind explains how their recommended charities help animals, reducing overcrowding, ending painful procedures without anesthetic, and pushing major companies towards better welfare. One of their partner groups even convinced McDonald's to move to cage-free eggs. And even a modest monthly gift goes a long way. Around $15 a month can help protect hundreds of animals a year. Because Farmkind is grant-funded, they cover their operating costs and support creators like me without ever taking a cut of your donation. Farmkind shows you exactly how many animals you're helping. Use the link in the description, and your donation will be matched 50% by a larger donor. Smoke rings. One of the most striking fictional explorations of zero-gravity living comes from Larry Niven's Smoke Rings novels, The Integral Trees, 1984, and its sequel, The Smoke Ring, 1987. Niven imagined a naturally occurring megastructure, a vast torus of breathable atmosphere orbiting a neutron star, the remnant of a gas giant planet that had been stripped and captured by the star's gravity. The result is a colossal ring of air tens of millions of kilometers across, circling in freefall with no planetary surface beneath it. Within this smoke ring, life exists entirely in microgravity. Plants evolve into kilometer-long structures, like the famous integral trees, that stretch across pressure gradients in the atmosphere. Instead of roots and trunks holding them upright, they flow in graceful arcs. Their ends drift in opposite directions, each tip forming a leafy forest canopy where life clings and flourishes. Humans, too, live here in small tribes, adapted to a world without up or down, traveling by swimming through the air, and using fire and rope as their primitive technologies. I should note that fire, much like water, acts very interestingly in zero-G. The smoke ring setting is compelling not just for its grandeur, but because it forces us to think about what biology and culture might look like when gravity is no longer a given. Niven's tribespeople must relearn the basics of survival in 3 dimensions, how to navigate, how to tether themselves, and how to adapt socially when territory is a drifting patch of vegetation in the sky. For readers, it's a vivid glimpse into how alien, yet plausible, a true zero-G ecosystem could be. Niven's not the only person to look at this idea either, so we see a variation in Peter Hampton's Commonwealth saga, and both authors explore ecology in such environs. Ecology in Zero-G. Life in microgravity does not behave as it does on Earth. Plants evolved with gravity tugging on every stem and root, and when that tug vanishes, circulation, pollination, and waste cycles no longer follow familiar patterns. Roots wander in all directions, water clings in floating blobs instead of soaking soil, and gases fail to stratify. Ecosystems in a bubble habitat would need careful engineering, fans and pumps to keep air and water circulating, genetic tweaks to help plants orient themselves, or even new kinds of crops designed to thrive in weightless space. That said, once those changes or augmentations occur, you have very nearly no size limit on many organisms. You still need mechanisms to transport nutrients and air around a large organism, which puts a size limitation on insects who have no lungs, for instance, but you could get trees that made a redwood look like a bonsai tree, and again growing out in a sphere rather than just up or down. In the bubble shell we discussed earlier, you could have trees that rose from the inner shell's ground 1,000 miles up the top shell to press the ceiling. Animals and microbes would need adaptation as well. Pollinators might take the form of swarming drones or modified insects that can navigate without up or down. Waste systems would be forced to rely more heavily on microorganisms and mechanical separators. Yet once these challenges are solved, entirely new ecological niches emerge, floating forests suspended in light, or coral-like gardens drifting in bubbles of nutrient mist. These are ecosystems that echo Earth's reefs or canopies, but freed from gravity's constraints. Culture with no top or bottom. For humanity, the shift is not only biological but cultural. A zero-G civilization will build its architecture without floors or ceilings, clusters of rooms and habitats arranged in 3 dimensions like reefs of stone and steel. Transportation becomes true 3D mobility, where roadways, elevators, and cranes are obsolete and people swim through space with equal ease in any direction. Psychologically, there would be a divide between floaters who live in this freedom and spinners who still prefer the stability of spinning gravity. Over generations, floaters might come to view gravity as a quaint affectation of their ancestors, who like to run around in circles all day, while seeing themselves as the real inheritors of space and freedom. Daily life would look alien to us but natural to them. Children would learn to orient by landmarks instead of up and down, and games might take place in full 3-dimensional arenas. Even basic gestures like pointing or standing might vanish in favor of drifting, tumbling, and tethering. To sinkers on Earth or in O'Neill cylinders, such a culture might look bizarre, but to floaters, it would simply be home. Fiction and imagination. Science fiction has given us glimpses of the future. Larry Niven's Integral Trees and Smoke Ring remain the best-known portrayals of zero-G ecologies, with entire tribes surviving in floating vegetation. Other authors, from Peter Hampton, who we already mentioned, to the creators of The Expanse, have touched on similar ideas. These stories remind us that imagining culture and weightlessness requires more than physics. It calls for rethinking society itself, from how people eat to how they raise their children, to how they define territory when nothing is fixed in space. A farmer tethering himself along drifting hydroponic vines, a worker in a bubble shipyard guiding kilometer-long beams with fingertip nudges, children chasing each other in spirals through a free-floating forest. Fiction lets us test these possibilities, and then science challenges us to turn them into reality. So what do we make of these bubble habitats and zero-G megastructures? On the one hand, they confront us with profound obstacles. Our bodies are not built for microgravity, and our ecologies assume the constant pull of Earth. Yet those problems are all solvable, whether through genetic engineering, mechanical assistance, or simple adaptation. On the other hand, they open the doors to a future that are profoundly new. Vast, airy worlds where reefs of plants float in sunlit bubbles, where trillions might live in structures the size of planets, and where humanity is no longer chained to the ground. Spin gravity habitats will always have their place, but to embrace the void itself is to embrace the wider universe. Zero-G megastructures remind us that the cosmos is not just something we stand on, it is something we can swim through, soar in, and inhabit in ways evolution never prepared us for. Floaters may one day see themselves not as Earthlings in exile, but as the true citizens of the great dark sea between the stars. And in that vision, we glimpse a future where humanity has learned not merely to conquer space, but to belong to it. And to belong in it.